9.8 meters per second squared. So we get 9.8, but we have to subtract 0.95, and we multiply that by 75 kilograms, and we get 664, I'll round it off to 660 newtons. 660 newtons. So 9.8 minus 0.95 times 75. So we'll get 660 newtons would be what the scale would read, something less than what the man actually feels with his own weight. Okay, in number D, what weight does the scale read when the elevator is traveling up, but he's slowing down? Okay, if the elevator is going up, but it's slowing down, that means it's deaccelerating. Again, it would have a negative acceleration of minus 0.95 meters per second squared. So this would be the exact same answer for number C. The acceleration is a negative number, and it's a minus 0.95. So again, even though it's going up, the elevator is deaccelerating, giving it a negative acceleration. So we would come up actually with the same answer for D. Okay. Number 4. Number 4. If a mechanic is exerting 97 Newton meter of torque on a nut, the torque is 97 Newton meter of torque, and on a nut, and is applying a 415 Newton force perpendicular, how far away is the center of a nut from grasping the wrench? So here's the nut, here's the wrench, distance r away, and here's the force. So the torque is simply r times the force. So the force is 415 newtons. So that simply means that the torque divided by the force is equal to this lever arm distance, which is 97 Newton meter, divided by 415 newtons. Realize the newtons cancel out, giving you meters, and you simply have that. So it would be 97 divided by 415, or 0.23 meters. Okay? So it's a fairly easy example of just applying this torque equation right here. Okay, question number 5. Two children balance on a seesaw. If the boy weighs a certain weight, if the boy, let's see, the boy's over here, here's the seesaw, and the boy weighs 352 newtons, and he sits 1.12 meters away. How much does the girl over here, weighs if she sits 1.34 meters away from the fulcrum? So this is a case where this is a torque situation where we have rotational equilibrium, and the sum of the torques must equal 0. We have a torque this way, wanting to swing the whole thing clockwise, which we'll call a plus, which will be this force, 352 newtons, times the radius, this radius here, 1.12 meters, and that's a torque wanted to bend the thing this rotated clockwise, rotated counterclockwise in the minus direction, we'll give it a minus sign, is some weight times this radius, 1.34 meters. And all this must equal 0. Therefore, we would have a 352 times 1.12 meters equals W times 1.34 meters, or W is simply 352 newtons times the ratio of 1.12 over 1.34. Notice the meters cancel out. And so the weight is simply this ratio, 1.12 divided by 1.34 times 352, or 294 newtons. So the girl must have that amount of weight in order to balance the seesaw. Okay, number 6. A captain of a ship holding a steering wheel. A captain holds a steering wheel and exerts, that's number 6. Here's the wheel and exerts 211 newtons of force with each hand. So basically, here's the wheel, and it's a wheel, but I'm going to draw it like this. There's a force going this way, and an equal force going this way, and this distance is 1.10 meters, 1.10 meters, so here's R, and the question is how much torque will he exert, okay, and this force is 211 newtons, and this force is 211 newtons, so it's like you have a steering wheel and you're yanking it to the right, so the sum of the force, the sum of the torque is, notice this is pulling the thing clockwise, so it's R times F, and this is pulling the wheel clockwise also. They're both going in the same direction. So it's actually 2 times RF. So it's 2 times 1.10 meters times 211 newtons. So it's double this. So whereas 2 times 1.1 times 211, and then we come up with a total torque of 464 newton meters, 464 newton meters. So both of these actually add to each other because both of these forces are trying to rotate this wheel in the clockwise directions, so they're additive. Okay. Number 7. A physics experiment is done in which 3 masses are used to balance, this is number 7, are used to balance a bar on a fulcrum. Let's see, we have, the question is where must the third mass be placed? So we have a situation like this. Here's the fulcrum. We have a 21 kilogram and a 12 kilogram. These two masses, this is 12 centimeters, and from here to here is 21 centimeters. 21 centimeters down to 12 kilogram mass and 12. And we have 18 kilogram over here, and the question is, what distance must this be? What should this x distance be in order to balance out this static problem? That's just another example of that the sum of the torques must equal 0. Rotating this in the clockwise direction would be this radius x, we'll call x, times 18 kilograms. And opposite, we have these, which are rotated in the counterclockwise direction. Given a minus sign, it would be, let's put this, well, this is in so many centimeters. Notice this is in centimeters. So we'll keep we'll keep the lengths all in centimeters. We could switch it to meters, but we can keep it in centimeters too. So if this is in centimeters, I'll just write this. As long as we use units that are consistent, it will work fine. So we'll have 21 centimeters times 12 kilograms minus, and this 12 centimeters times 21 kilograms. Okay, so x, 18, if I'll think of it as an algebra equation, 18x equals 21 times 12 plus 12 times 21. It's interesting how that works. The numbers, how numbers work out. So x is simply, I'll just go ahead and multiply this out. 12 times 21, and it's twice that, so it's 882, and it's divided by 18, or 49 centimeters. Okay. 49 centimeters, and is that the answer? I have the book here says, I may have that the wrong, let me check the answer of the book, just to be on the safe side. I may have written down that I have the answer wrong, but let me go and see. Solution to the, let me see what the book says. This is number 7. Let's see, 18, 12 kilogram, 21 kilogram, 21 centimeter, 12 centimeter. The book has that the answer is 28 centimeter. Let's see. Let me see, maybe I didn't multiply this right. 21 times 12. Whoops, I didn't. 21 times 12 is 252. Then I have two of them, which is 504. I multiplied these wrong, divided by 18, which is 28. See, I often multiply numbers incorrectly myself because I key them in wrong. a common problem with students. I understand that. I used to, when I was a student, just simply key in the wrong number. Quite often, actually. That can lead to the wrong answer. But, again, even if you key in the wrong number to the question, to the problem, the important thing is that you have the method right. So the answer actually is 28 centimeters. Okay, number 8. Actually, number 8 and 9 are very similar. So what I'm going to do is we're going to set up the problem for do 8 and 9, and we'll do 9. We'll do 8 first, but then we'll do 9, but we'll just use the same diagram for both. And then we'll just go on from there to solve number 10. Okay, in this case, we have an inclined plane. We have inclined plane, and we have a block sliding. And this angle here is 23 degrees. The mass is, let's see, 30.1 kilograms, and the angle is 23 degrees. And the basic question for both of them is, what is the acceleration of the block? What is the acceleration of the block? And in question 8, we assume no friction. In question 9, we assume that there is friction, and the kinetic coefficient of friction is 0.35. Okay, so that's the problem. Now remember, to solve this kind of problem, we have to break it up into parallel, the sum of forces that are parallel to the plane, and the sum of forces that are perpendicular to the plane. Okay, so the weight which acts down, I'm going to draw that the weight acts from here and acts down. I'm going to just conveniently draw it all the way down to here. That's the weight, which is mg. Okay, and I'm going to say that we're going to draw a parallel there's a parallel component and a perpendicular component. The perpendicular component comes like this, where this, I'm going to call this weight parallel, and this weight perpendicular. Okay, so notice that this angle here, this is a right angle. That's a right angle. So this angle would be an alpha angle, where alpha plus theta is 90 degrees. So that means this is also theta. So this angle here, this little angle here, is the same as this angle. If this is theta, then this is theta. Which means that this perpendicular is simply W. This is the full W times the cosine of the angle. It's this W, the length of this, times the cosine of this angle. Okay. The parallel component, I'll write that down here. The parallel component, the parallel weight, is W times the sine this is also this component down here. It would be the sine of this angle. W times the sine of the angle. Okay, now we're all set to look at the normal. The normal. There's a normal force acting up. And first of all, we look at the sum of the forces that are perpendicular to the plane. And what do we have? We have the normal force which acts up perpendicular to the plane, and we have what acting down is the weight perpendicular, and the sum of these is 0. The block is not moving up or down, it's only moving parallel to the plane. So that means that the normal force equals this perpendicular weight, which is the weight times the cosine of the angle. Okay, so let's go ahead and we can go ahead and put numbers if we want into this. Well, we won't do it yet. We won't do it yet. I like to solve algebraically everything first anyway. So now the second equation is we look at the sum of the forces that are parallel to the plane. And what do we have? We have this weight parallel, which acts this way, and in the opposite direction we have the friction. Okay, so we have the friction which acts in the opposite direction, and that's equal to mass times the acceleration, because this object is potentially accelerating down the plane. Okay? So, and the friction here, as we know, is the kinetic coefficient times the normal force, where that's normal force, or it's the kinetic coefficient times the weight times the cosine of theta. So the weight, this parallel weight is W. Remember, this parallel weight is W times the sine of the angle, okay, minus the kinetic coefficient times W times the cosine of the angle equals mass times acceleration. Okay, now we've written out all the equations really for question 8 and question 9. Question 8 is simpler. Question 8 is assume there's no friction. Well, if there's no friction, then what do we have? We have this whole term here. This whole term here is 0. A big fat 0. So we're going to assume that there is no friction, so this whole term goes away. So what we have is we have just what's left, that W or mg times the sine of theta equals ma. Notice the m's cancel out, and I think you can read this, that I'm going to erase this right up here, that basically g times the sine of the angle is equal to the acceleration. A very simple expression, really. So if we have 9.8 meters per second times the sine of the angle, sine of 23 degrees, that's the acceleration. Notice we don't even have to enter in key in the mass. So and this would be for question number 8 here. So 23, the sine of 23 times 9.8, and we get 3.8 meters per second squared for the acceleration in question number 8. And it's going down. We can say it's a minus acceleration because it's heading down the ramp. 3.8 meters 3.8 meters per second squared, accelerating down the ramp. That's for question 8. That's assuming there is no friction. But what if now, that's for number 8. I'm going to erase this now, and let's solve the more general case where there is friction. Where there is friction, now we do have to consider this. So I'm going to write this equation out again, where mg times the sine of theta minus the coefficient, kinetic coefficient of friction, times weight, W is mg, times the cosine of the angle equals mass times acceleration. So notice for W here, wherever there is a W, I simply put mg, and I put a mg here. Mass, mg times the sine of the angle, minus, this is the friction right here, equals mass times acceleration. Going to erase this. Notice we can cancel the mass out. So again, even though we're given the mass, we don't actually need to necessarily use it. In this case, we actually don't need to use it. And we get that g times the sine of the angle minus the kinetic coefficient of friction times g times the cosine of the angle equals the acceleration. So let's go ahead and plug these numbers in. 9.8, and this is in meters per second times the sine of 23 degrees minus coefficient is 0.35, 0.35 times 9.8 times cosine of 23. All that equals the acceleration. So let's pull out the calculator, and I'm first going to calculate this term here. 23 times cosine of the angle, or excuse me, cosine of 23 degrees times 9.8 times 0.35, and I get a minus 3.16 roughly. Store that in my little calculator here. And then 23, and the sine of that 23, times 9.8, and I subtract this term, and I get the acceleration is equal to minus 0.67 well, it's 0.67 meters per second squared. So you might get a slightly different number depending on exactly how you calculated it and what you rounded off, but this is what I would get, assuming I punched in these numbers right. You might check me on that. Okay, I'm going to move on to notice that again the acceleration is it's a negative number really, but it's down. It's down. We can give it a negative number, but it's less than what we had before in question number 7 because of the friction. So the friction slows it down. Okay, the last problem is question number 10. And we have one of these situations where two boats are being pulled with by a string together. So we have, we'll call it M1, being pulled by M2, which is being pulled with a certain force of 3.1 newtons this way. So this is number 2 is 0.32 kilograms, and number 1 is 0.45 kilograms. And let's see, these are tied together. A child sits in the bathtub, these are really boats, and he pulls it with a force of 3 point. So we know what this force is. This force is 3.1 newtons to the right. What is the acceleration? The question is, what is the acceleration, and what is the tension? This tension in between the two boats. So notice that the rope is under tension. So this if we do a diagram, a body, just a free body diagram right around M1, what we would see would be this. We would see the M1 ship and is being pulled with a tension